It's a whopping 1300 episode. Hooray, hooray, hooray! A cheer and most welcome everyone to this centennial episode. A 1300, that is in itself quite amazing. Congrats everyone for the patience and the development the last 100 and of course hundreds has been quite amazing. The opening up that Smolin and Roberto Unger supplied is just beyond expectation. I would never assume that to happen. I'm so glad for it. I don't even know what it will affect, but all the other lectures that I've done before are sort of blossoming now. And I think of a lot of what we've gone through, which is extensive. I think it's closing to be unbeatable, at least on the net. The expanse, the broadness and the depth. And that is multiplied definitely by Roberto Unger. Definitely. I continue with the landscape problem, and I hope it will become clearer now. At least some clarity will be gained. What could be better to make the Jubilee lecture with Roberto Unger and Smolin's grand scheme. I continue where I took off. Note that if a proposal to resolve the landscape problem does not satisfy conditions 1 and 2, it cannot be considered to be even a candidate for a solution to the landscape problem. The landscape problem represents a curious crisis in the development of science. Its solution requires, as we shall see, the construction of speculative cosmological scenarios, which posit regions or epochs of our universe for which we have presently no observable evidence. Nonetheless, we must insist on taking seriously only scenarios and hypotheses that make falsifiable or strongly verifiable predictions. Otherwise, people can just make stuff up, and the distinction between science and mythology becomes porous. To do so is very challenging. This is hard, serious science, and it cannot be rushed. As challenging as this situation is, there are two reasons for optimism. One is that there already are candidate solutions that make real, falsifiable predictions. Some of these predictions involve features of the CMB that code information about a cosmological epoch to the past of our Big Bang. This possibility of making observations which test hypotheses about past epochs is the second reason for optimism, and I will discuss examples below. So there is no need to despair. Meanwhile, special pleading that the standards of science should be lessened to admit explanations with no falsifiable consequences in order to keep alive a bold speculative idea should be strongly resisted. While speculation has its place in science, ultimately science is not interested in what might be true. It is interested only in what can be convincingly demonstrated by deductions from observational evidence. I should stress that the landscape problem, while it arose in string theory, is likely to be there whatever the fundamental unification of physics turns out to be. There is no evidence from any approach to quantum gravity that mathematical consistency or the existence of a low energy limit restricts the matter content of theory. In loop quantum gravity and spin foam models, it appears that the theory is consistent with coupling to a large set of gauge groups, fermions and scalar fields. But the strongest reason to expect the landscape problem is not an anomaly of string theory, is that it has deep historical roots, which I sketch in the next section. It might have been anticipated a long time ago, and indeed it was. These historical roots of the landscape problem suggest that the landscape problem was bound to occur as physics progressed. As I will argue, it is an inevitable consequence of the general form we have assumed for physical theories since Newtonian mechanics. Thus, whether string theory is correct or not as a hypothesis about unification of the fundamental forces. The landscape problem is likely to be a feature of whatever correct theory it replaces. Therefore, the future of theoretical cosmology will to a large extent hinge on finding the correct scientific resolution of the landscape problem. After the historical sketch I explain in chapter 3, the three main options for cosmological settings within which a solution to the landscape problem might be situated. These options are evaluated in section 4. As our knowledge of elementary particles and fundamental interactions grew dramatically during the 20th century, we began to be interested in questions that are not answered by knowing the laws of physics. One of these is the question, why are these laws rather than other possible laws? If there are many possible laws, each as logically consistent as those we observe, what select the laws that are realized in our universe? Another question not answered by knowing the laws is what selected the initial conditions at or near the Big Bang. These questions bothered a few physicists and philosophers long before Strominger uncovered the landscape problem within string theory. Within living memory, the idea of the evolution of laws was energetically championed by John Archibald Wheeler, who was uniquely a pioneer of both nuclear physics and the quantum theory of gravity. In the 1960s, Wheeler contemplated that bouncing of black hole singularities to new universes. By a bounce, he meant that quantum effects would eliminate the singularities of classical general relativity and lead regions of space-time tending to future singularities to expand again, thus forming new regions of space-time to the future of where those singularities would have been. He further hypothesized that the laws of physics, or at least their parameters, were reprocessed on each such instance. A generation earlier, Dirac had proposed that the law of physics may evolve. At the beginning of time, the laws of nature were probably very different from what they are now. Thus, we should consider the laws of nature as continually changing with each epoch, instead of as holding uniformly through space-time. Why were these great scientists drawn to speculate that laws evolve? The reason is that, absent a principled explanation for the laws we find, the evolution of laws is a necessary part of any explanation of the why these laws problem. There are in science only two ways to explain why some state of affair has come about. Either there are logical reasons, it has to be that way, or there are historical causes which acted over time to bring things to the present state. When logical implication is insufficient, the explanation must be found in causal processes acting over time. This was understood clearly more than a century ago by Charles Sanders Peirce, the founder of the school of philosophy called American pragmatism. To suppose universal laws of nature capable of being apprehended by the mind and yet having no reason for their special forms, but standing inexplicable and irrational, is hardly a justifiable position. Uniformities are precisely the sort of fact that need to be accounted for. Law is par excellence the thing that wants a reason. Now the only possible way of accounting for the laws of nature and for uniformity in general is to suppose them results of evolution. Peirce is insisting that it is not enough to know the laws of nature. He is demanding that there be explicable reasons for the laws of nature themselves. This demand has a long precedence in the history of science. It was most clearly articulated by Leibniz, who enunciated this: the principle of sufficient reason. For every property of nature which might be otherwise, there must be a rational reason which is sufficient to explain that choice. Leibniz makes it clear the kind of sufficient reason he has in mind must be something beyond mathematical consistency. The great foundation of mathematics is the principle of contradiction or of identity. That is to say, that a statement cannot be both true and false at the same time, and that A is A and cannot be not A. And his single principle is enough to prove the whole of arithmetic and the whole of geometry. That is to say, all mathematical principles. But in order to proceed from mathematics to physics, another principle is necessary. As I observed in my theodicity, that is the principle of sufficient reason. That nothing happens without there being a reason why it should be thus rather than otherwise. If no reason can be given, the choice must be a false choice. For example, no rational reason can be given for why is the universe where it is and not 10 feet away to the left. From this, Leibniz draws the conclusion that space must be relational, so that only relative positions within the universe are physically meaningful. Physicists use the principle of sufficient reason in this negative way when we show that two gauge equivalent configurations of the electromagnetic or gravitational field refer to the same equivalent, same physical state. Otherwise, one would not have unique deterministic evolutions of fields. This was the essence of Einstein's whole argument that led him to conclude that diffeomorphism invariance is a gauge symmetry. And it was also the basis of Dirac's influential work on the gauge invariance in constrained Hamiltonian systems. What can count as sufficient reasons for laws of nature? The landscape issue is precisely the fact that mathematical consistency alone cannot account for the choice of the laws we observe governing phenomena in our universe. Peirce is saying that if we demand sufficient reason for the choice of laws of nature, we can only answer successfully by positing that the present laws are the result of evolution from a past when the laws were different. To put Peirce's argument in one line, laws must evolve to be explained. Unevolving laws cannot be explained. So you see the problem for the Newtonian paradigm. The laws are left unexplainable. Sufficient reason for cosmological initial conditions. We can also apply Leibniz's principle of sufficient reason to the problem of the selection of the initial conditions of the universe. It is a fact that in general relativity, and presumably in any field theory of gravitation, there are an infinite number of solutions of the field equations, which have an initial singularity. To apply general relativity to cosmology, it is then necessary to give the initial conditions at or shortly after the singularity. The choice of initial conditions requires explanation. If we are optimistic and believe all questions about the universe are answerable, then that explanation must satisfy the principle of sufficient reason. If no sufficient reason can be given within a given theory, then that theory must be wrong. It is one thing for general relativity to have an infinite number of solutions in the asymptotically flat case. For these correspond to idealized approximate descriptions of subsystems of the universe. These come in many copies, so the theory must have many different solutions. But why should a cosmological theory have an infinite number of solutions when there is only a single universe? Why does general relativity so extravagantly overperform its job, giving not just predications for the actual universe, but also predictions for an infinite number of universes that never exist? The only conclusion to draw is that general relativity is not the correct cosmological theory. It is at the very least to be supplemented either by a theory of initial conditions or by an historical explanation which explains why such special initial conditions were picked out for realization in the one real world. The common roots of the landscape problem and background independence. I bring up Leibniz's principle of sufficient reason because I believe it helps greatly to clarify the issues that we confront in seeking a solution to the landscape problem. In particular, the principle of sufficient reason not only tells us that laws must evolve to be explained, and that there must be a dynamical explanation for the initial conditions of the universe. It greatly constrains the context in which we seek those dynamical explanations, which led to the selection of the laws and initial conditions of our universe. This is because the principle of sufficient reason singles out a class of theories of space and time, those that are relational and background independent. Thus, the landscape problem and the problem of making a background independent quantum theory of gravity and cosmology are profoundly linked. conceptually and historically, both have their roots in the principle of sufficient reason. This is seen in several corollaries of the principle of sufficient reason that are highly relevant for the contemporary search for an explanation for the selection of the observed laws of physics. One, space and time are relational rather than absolute. Leibniz used the principle of sufficient reason heavily in his debates against Newton's concept of absolute space. And time. These arguments were elaborated by Mach and became the motivation for Einstein's invention of general relativity. The principle of the identity of the indiscernible. This holds that there cannot be two entities in the world with exactly the same properties. If all properties are relational, then to identify a particular elementary particle is the same as giving a list of all its properties, including its relative position in space and time. Causal and or explanatory closure. This is the demand that all chains of causes and chains of explanations for events of the universe close within the universe. A cosmological theory must be spatially compact without boundaries. This is a consequence of the previous principle, because if one has to impose asymptotic boundary conditions to get a solution to a field equation, then chains of causation point outside the universe. The only way to avoid having to input boundary conditions to determine a solution to general relativity or any other field theory is to not have any spatial or null boundaries. This was the reason Einstein introduced spatial compact solutions for general relativity and insisted on their use in the modeling cosmology. No unreciprocated actions There should be no entity which acts on dynamical degrees of freedom, which is not itself a dynamical degree of freedom, which is acted back on in return. This principle was used by Einstein to motivate his rejection of absolute space in favor of a theory general relativity, in which the geometry of space-time is a dynamical degree of freedom. Another way to say this is that there must be no absolute or ideal entities whose properties influence the evolution of degrees of freedom, which are themselves not dynamically determined. And then we are coming into background independence, but we better end here. You see, by taking away the landscape, we're not gaining, we are losing. And the landscape is not unimportant. It is oddly people for thousands of years assume the landscape to be uninteresting, or at least something that you could do without. Obviously, this is not the case. There is a similarity. In the landscape problem, we're taking away the background, and in the Newtonian paradigm for cosmology and cosmogony, we are taking away the inside and look at the outside in a way that is just paradoxical, nonsensical in some ways. I say thank you very much. Thank you for joining for the 1300. And well, see you soon again. Do enjoy. I hope it wasn't too demanding on the thinking skills. This is pretty amazing as it is. So do put some effort into this and you will be greatly awarded. It will be like a flower that starts to bloom. You will see all the petals and it will have a glorious shine of understanding. Thank you very much and have a very pleasant afternoon. Bye-bye. And here you can see sun is coming up. The sun, which is a really rare visitor this year. The cold, it comes out. It's a high pressure.